What happens if a pump keeps running while a valve suddenly closes? In industrial systems, this can create a dangerous pressure spike in seconds. Pipes can vibrate, equipment can be damaged, and production can stop before the plant even starts operating. Unsurprisingly, many of these problems are discovered during commissioning, when the plant is already built. At that point, fixing the issue can take weeks, sometimes months, because replacing a pump or redesigning a piping system is expensive. So the question is, what if we could test all of this before the system even exists? Today, we are going to connect a real PLC, an industrial HMI, and a physical-based simulation to create a cyber-physical digital twin of pumping system. Let's start with the architecture. At the center of the system, we have a PLC. The PLC communicates with a PanelView operator interface and a physics simulation running in NVIDIA Isaac Sim. All devices are connected through Ethernet. The PLC exchanges data with a simulation through a Python interface built using the PyLogix library. This interface reads and writes PLC tags in real time, allowing the control system to interact directly with the physics model. In a real installation, the pump will be controlled by a variable frequency drive. In this setup, we use a PowerFlex 525 drive inside the PLC project. However, this specific drive requires 480 volts three-phase power, which is not available in this lab. So instead of driving a real motor, the PLC command controls the pump speed inside the simulation. The PLC still behaves exactly as it would in real time. The only difference is that the pump exists inside the digital twin. Now let's look at the physical process. The pump moves fluid through a pipeline from one tank to another. But the fluid encounters resistance along the way. That resistance comes from several sources: pipe friction, valves, elbows and fittings, and elevation difference. Inside the simulation, the fluid is represented by the particles. Their velocity represents the flow rate in the system. When pump speed increases, the particles accelerate. When resistance increases, the flow slows down. This allows us to visualize hydraulics behavior directly inside the digital twin. Behind the visualization, the system relies on simplified hydraulic calculation. The model uses real engineering parameters such as fluid density, pipe diameter, pipe length, friction factor, and valve loss coefficients. The pump itself is represented by a simplified pump curve. This curve describes how the pump head decreases as the flow rate increases. The pump model is based on simplified pump performance curves derived from typical pump datasheets. At the same time, the pipe introduces hydraulic losses. These losses depend mainly on the square of the flow rate. By combining the pump curve with this system resistance, we can compute the operating point of the system. And because the model is lightweight, this calculation can run in real time. Another important aspect of this digital twin is how the system is structured. Instead of building a single large simulation, each piece of equipment is implemented as an independent simulation block. For example, the pump, the valves, the pipeline, and the sensors. Each of these components contains its own behavior and parameters. This approach is what I call OOIDT, Object-Oriented Industrial Digital Twin. In this model, industrial equipment becomes reusable simulation object. A pump object can contain hydraulic equations, operating limits, control inputs, and sensor outputs. Because these components are modular, they can be reused in many different simulations. For example, the same pump model could easily be integrated into a completely different process simulation. This modular architecture allows digital twins to scale from small experiments like this one to full industrial processes. Now let's look at the control system. The flow rate is controlled by a PID loop running inside the PLC. The operator defines a flow set point. The PID control continuously adjusts the pump speed to maintain that target. In a real installation, the PLC will send this command to a VFD. Here, the command is transmitted to the simulation. The simulation recalculates the hydraulic behaviors instantly. As pump speed increases, flow increases. As resistance increases, flow decreases. This creates a real-time cyber-physical feedback loop between the PLC and the digital twin. Another important part of this experiment is the industrial network itself. The digital twin is not running in isolation. The PLC, the HMI, and the simulation are exchanging process values over Ethernet in real time. Using Wireshark, we can observe these packets directly on the network. The operator interacts with the system through a PanelView 800 HMI. From this interface, the operator can start and stop the process, adjust flow set point, monitor pressure and flow, change the percentage of the modulating valve, and observe alarms. The HMI also displays a real-time trend graph showing how pressure and flow evolve over time. For this demonstration, the HMI is accessed through a VNC connection, so we can visualize the screen directly from the workstation. In a real industrial environment, remotely access like this must be carefully secured. In architectures based on the Purdue Model 2.0, this connection will typically pass through segmented zone or secure gateways. Let's start the system. The operator presses the start button on the HMI. The PLC activates the control logic. The PID controller begins adjusting pump speed. Inside the simulation, fluid particles start moving through the pipeline. As the pump accelerates, the particles move faster. The calculated flow rate is sent back to the PLC and displayed on the HMI in real time. This is where the cyber-physical interaction becomes visible. The PLC influences the physical model, and the physics model continuously feeds data back to the PLC. Now, let's simulate a real industrial problem. Imagine that a valve suddenly closes while the pump is running. When the valve closes, the resistance in the pipeline increases dramatically. The flow begins to drop, but the pump still pushing energy into the system. So the pressure starts to rise. Inside the simulation, we immediately see the effect. The particles slow down and the restriction increase. At the same time, the PLC detects the abnormal pressure condition. The HMI triggers a high pressure alarm, warning the operator. Because the system is connected in real time, we can see the pressure rise directly on the crane graph. This shows exactly how the system responds to unexpected operating conditions. By combining automation hardware with physics-based simulation, engineers can test critical scenarios before commissioning. This approach allows teams to validate pump sizing, analyze hydraulic losses, test control strategies, evaluate operator response, and better understand network cyber-physical behavior. Instead of discovering problems on site, engineers can move this validation to the design phase. Cyber-physical simulation is not just about visualization. It connects automation systems with engineering models to understand how industrial processes truly behave. By validating the physical behavior, control logic, operator response, and communication flow before startup, engineers can significantly reduce commissioning risks. And this experiment is just one example of what becomes possible when automation and digital twins work together. If you are interested in industrial automation, digital twins, visual commissioning, or OT cybersecurity. This is an area evolving extremely fast.